So in between, I will ask you to unmute Shreya to just to understand whether all of you are on same page. Uh, Now let us go ahead with what we were discussing in the class. So parameters for a balance section. Uh, just a minute. N is missing here in this spelling. So parameters for balance section, and we were discussing moment of resistance factor RU. So we had derived the expression mu is equal to 0.36 FCK XUP into bracket D minus 0.416 XUP. So in last class, I have already discussed that this part of this expression is nothing but the compressive force Cu, and this part is nothing but the lever arm. So let me draw the bending stress distribution diagram for the reference. So if I draw the bending stress distribution diagram, this is the cross section. Uh, Let us say the cross section is rectangular cross section. It looks something like this. Uh, and that cross section, when viewed from the side, it looks like a line. So I have drawn that. Just give me a second. And we have reinforcement. We have reinforcement placed here. 1, 2, 3, and let me also draw the fourth bar. Oh, 1 minute. 2, 3. So let us say there are 3 bars placed in one layer. So we have already discussed that the distance from extreme compression fiber, that is from here till here, that is centroid of the steel group. This distance just give me a second. This distance is effective depth, and we denote it by notation small d. And the neutral axis, let us say it is located. Shreya, is everything audible and is everything visible?
Yes, sir.
Okay. And let us say that the neutral axis is located somewhere here. So this is the location of neutral axis, and distance of neutral axis from the extreme compression fiber. We already know that this distance, we denote it by the notation XUP. Shreya, are you with me?
Yes, sir.
So U stands for ultimate and P stands for balance section. So this is the location of neutral axis when the entire beam is designed as the balance section. Now, if I look at this cross section in the side view, uh, that means uh, so if I look at this cross section from this side, are you able to see the laser pointer?
Yes, sir.
So if you look at this cross section from this view, it will look like a line which I have shown here. And on this line, now let us draw the bending stress distribution diagram at failure. So how does bending stress distribution diagram at failure look like? So we are aware that it looks something like this. Just give me a second. This being the first online class after a long time, we will struggle for a bit, then we'll continue. So, from strain level equal to 0.0035 till strain level of 0.002, which happens somewhere here, uh, the variation is going to be constant, the stress is going to be constant, and then it is going to vary parabolically. So it looks something like this. This is how the variation will look like for the bending compressive stress. You have to understand that this parabola goes and connects at neutral axis at neutral axis it has a zero stress. Are you with me, Shreya? Okay. And what is the value here? So at the extreme compression fiber at failure, we have the value of stress equal to 0.446 FCK. This all we have already discussed. So let me write down that value. So here the value of stress is 0.446 FCK. Are you with me?
Yes, sir.
And on tension side, the entire concrete on tension side needs to be neglected. Only the element that offers resistance in tension is the steel nearer to the bottom face, and at the level of steel, therefore I am going to show the resistance offered by the steel, and that is tensile resistance. So it is going away from the cross section. So if I show it on the left hand side of this line, it is going away means going towards right. If I show it on the left hand side of this cross section, then it is going towards the left. It has to go away from the cross section. So I will show that tensile resistance or tensile stress in this fashion. Are you with me, Shreya?
Yes, sir.
And how much is this tensile resistance? It is nothing but Fy upon 1.15, which is partial safety factor for the strength. But we know that 1 upon 1.15 is 0.87. So it turns out to be 0.87 Fy. Are you with me?
Yes, sir.
So let me write down that 0.87 Fy. So 0.87 Fy is the stress, and 0.446 FCK dropping down to 0 is the compressive stress. So corresponding to this compressive stress block, we are going to have a total compressive force which acts at the centroid of this stress block, that I am going to show something like this. This is the maximum compressive force this section can offer when it is on verge of failure. I'm going to call it as Cu. And at the location of steel, the stress is 0.87 Fy. If I multiply it by the area, I get the maximum tensile resistance, tensile force that is offered. I call that tensile force as Tu. So I'm going to call it as Tu. And we already discussed for equilibrium, if I apply summation Fx equal to 0, Cu minus Tu has to be equal to 0. That means Cu has to be equal to Tu. Are you with me till this point, Shreya?
Yes, sir.
Okay. So now how do we write down the moment of resistance offered by this cross section? So there are two parallel forces. One is Cu and another is Tu. And these two forces are equal in magnitude, opposite in direction. They are separated by perpendicular distance, which is this much. So what do we have to do in order to write the moment? So ultimate moment that this cross section can resist will be equal to magnitude of either Cu or Tu multiplied by lever arm. Happy, Shreya?
Yes, sir.
Okay. So what is the magnitude of Cu? That magnitude of Cu we have already derived that as 0.36 FCK B XUB. where XUB is the location of neutral axis from extreme compression fiber. FCK is uh, characteristic compressive strength of concrete. B is the width of the section. So let me also draw B here. So let me draw. Let me call this as B. Happy? Okay. So 0.36 FCK XUB is the value of CU. I could have as well written the value of TU, but we know CU equal to TU. So I can write either CU or TU. So I have chosen CU. So 0.36 FCK BXU. As the compressive force is offered by the concrete, you can see it depends on the concrete's characteristic compressive strength. And there is no term involving yield stress of the steel because I am writing CU, not TU. All right, Shreya?
Yes, sir.
Okay, so now let us write down the lever arm. So how much is the lever arm? So to write the lever arm, I need to write this distance, this perpendicular distance between line of action of CU and TU. So where does the CU act? CU acts at the centroid of this stress block. And where does the TU act? TU acts at distance D from extreme fiber. So how much is this distance from extreme compression fiber till CU? So we have already discussed that in the last class that distance is 0.41. This distance is 0.416. This distance I am talking about. Just a second. Yeah, this distance we know it is 0.416 XUB. So centroid of this parabolic and rectangular stress block effectively lies at distance 0.416 D. So let me mention that 0.416 D. 0.416 D. So what is the distance between perpendicular distance between line of action of CU and TU? It will be D minus 0.416 D. Minus 0.41, no, not 0.416 D. I'm sorry, it is 0.416 XUB. So let me clear that. Not 0.416 D, it is 0.416 XUB. So let us copy this here. So what is the lever arm? D minus 0.416 XUB. Are you with me, Shreya? Shreya?
Yes, sir.
Okay. So MU is this CU into lever arm. And then what we have done is XUB is written as KUB into D, where KUB is the neutral axis factor. Yes, Siddhi, I think you have messaged me. Anyway, so let me write down that. Just a second. Uh, so XUB is equal to KUB multiplied by D. So for multiplication, I'm going to use this sign, and for and if it is XUB, I'm going to use the capital X. So please keep track of these notations. XUB is KUB times D. What is KUB? KUB is nothing but neutral axis factor for balance section, and we have derived the expression for those as well. So let me substitute these values, this value in the value of MU. So once I substitute this value here, what happens? This expression becomes 0.36 FCK B KUB into D, then D minus 0.416 KUB into D. So I can take then D common, so that D comes outside and gets multiplied by 1D outside and becomes D square. So let me rewrite this expression. So then mu becomes equal to 0.36 FCK into KUB into bracket 1 minus 0.416 KUB, this multiplied by BD square. BD square. So this is the expression. And then we have already discussed in last class that this expression clearly bifurcates two things. BD squares is a geometric property and 0.36 FCK KUB into bracket 1 minus 0.416 KUB is material property. So we call this constant as moment of resistance factor RUB. So I have written RU. You have to understand that it is RUB because we are writing it for balance section. So this factor up to this, we call it as RUB. RUB, which is nothing but neutral axis factor for balance section. And then for various grades of steel and for various grades of concrete, we have computed the value of this neutral axis factor. Are you with me, Shreya?
So,
Okay. So you already have the table which reports the value of this neutral axis factor for various grades of steel and concrete. So let us quickly look at the unit of RUB. The unit of B and D square will be mm cube because I am going to substitute B and D in mm. So B is mm, D square is mm square, mm into mm square is mm cube. And the unit of moment of resistance has to be unit of force multiplied by unit of length. So this has to be in Newton mm. So whatever is the unit of RUB, whatever is the unit of RUB, it should be in such a fashion that the left hand side assumes the units of moment, that is Newton mm. So the BD square is mm cube. I have to multiply it with the unit of RUB such that the product is Newton mm. So what should be the unit of RUB? So we already discussed the unit of RUB should be Newton per mm square. So RUB will be in Newton per mm square multiplied by mm cube. So mm square gets cancelled and what remains is mm. So Newton mm will be the unit of RHS. Newton mm will be the unit of LHS. Therefore, uh, in order to have dimensional homogeneity of these two sides, we must have RUB expressed in terms of Newton per mm square. Now for various grades of steels and for various grades of concrete, we have already derived the values of this RUB. And for various grades of steel, we have already derived the value of KUB. So we have everything ready with us in tabular form as far as KUB and RUB is concerned. Are you with me, Shreya?
yes.
Okay. Now, this was all quick recap as this was the first lecture. I took some time to get acquainted with the whiteboard and everything. Now let us go to the next part of this session, and that is uh, just a second. Uh, this is zoom in, zoom out, next page. How do I go to the next page? Hmm, that's peculiar. Just give me a second. This is zoom in. This is fit to the width. This is zoom out. How do I add a page? 1 minute. Okay. Mm, fine. I think I will simply write here. So now let us go ahead with the next parameter. So as I said, we will be solving the numerical examples on each of the parameters, but next parameter being linked to moment of resistance factor. Therefore, we will discuss the next parameter first. This moment of resistance factor was the second parameter that we derived for second or third parameter. That third, am I right, Shreya? Shreya,
Yes, sir.
it
Yes, sir.
is third parameter, right?
Yes, sir.
Okay, so this is third. And now let us write the fourth parameter that we will be discussing, and that is uh, area and percentage of steel for balanced section. So the question that I am asking myself here is how much should be the percentage of steel such that the balance section is on such that the section is designed as a balance section. So what do I mean by that? So as we are aware mu is written as either cu or tu into lever arm. So we have written it first in terms of cu uh, and we got the one parameter, that is RUB, moment of resistance factor. Now let us write down this mu itself in terms of tu instead of cu. We will get the area or percentage of steel required to make the section balance. Are you with me, Shreya?
Yes, sir.
Okay, so let us go ahead. So I will write mu is equal to now tu multiplied by lever arm. Instead of writing it as cu multiplied by lever arm. And we already know that uh, tu is 0.87 Fy. The stress here is 0.87 and the area of steel that I am going to provide, I will call it as ASTB. What does S stand for? S stands for area of steel. What does T stand for? It is the area of steel provided on tension side of bending. Because the beam is subjected to sagging, the bottom face will be subjected to tension. So area of steel provided on tension side of bending, and B stands for balance section. So area of steel to be provided on tension side of bending such that the section becomes balanced is ASTB. Are you clear of this notation, Shreya?
Yes, sir.
Okay. So this area of steel I have shown schematically as 3 bars in one layer, but it may so happen that it may be more number of bars in more number of layers. That's absolutely all right. But this area of steel, I'm going to call it as ASTB. Happy? Are you with
Yes.
me? Okay. So let us go ahead. Now let me write down this TU. So how do I write TU? This stress is 0.87 Fy and I have to multiply it by area of steel. But as I'm interested in finding out area of steel for balance section, I will call it as ASTB. Happy?
Yes, sir.
So 0.87 Fy ASTB is nothing but TU. The lever arm won't change. The lever arm is going to remain the way it was earlier. So therefore, I can as well write this as D minus 0.87 416 XUB. Are you with me?
Yes, sir.
So this is the expression for moment of resistance when written in terms of TU instead of in terms of CU. Happy?
Yes, sir.
Uh, Now, uh, I already know that for equilibrium of this section, if I do summation fx equal to 0, which I will write now, summation, this is the sign for summation, fx, all the forces in x direction, this must be equal to 0 as the beam is in equilibrium. So if this has to be satisfied, that means we must have, देखो अब CU is towards left, so I will give a negative sign. TU is towards right, I will give a positive sign. So the forces acting on the cross section are CU, which is negative, plus TU, which is positive. This must be equal to 0. Happy?
Yes, sir.
So that what does that say? So that means that I must, therefore, I must have CU must be equal to TU. Happy?
Yes, sir.
Now, do we have the expression for CU? The answer is yes. What is the expression for CU? देखो 0.36 FCK B into XUB, isn't it? So let me write down the expression for CU. CU is nothing but 0.36 FCK into B into XUB, where XUB stands for position of neutral axis for balance section. 0.36 FCQ. This must be equal to TU. But what is the expression for TU? Tell me. The expression for TU is this 0.87 FY ASTB, isn't it? Shreya?
Yes, sir.
Yeah, so TU is 0.87 FY ASTB. So these two must be equal. So can I now get the expression for ASTB? ASTB therefore must be equal to 0.36 FCK B XUB, this divided by 0.87 FY. 0.87 FY. Are you able to understand this?
Yes, sir.
So this is the expression for a area of steel required to make this section balanced. Now, here lies a factor XUB, that is the position of neutral axis for balance section on right hand side. Now, what should I do? I should replace that XUB by neutral axis factor KUB multiplied by D, isn't it?
Yes, sir.
So let me do that task. So let me replace. Uh, let me say ASTB will be now equal to, what should I write? 0.36 FCK uh, KUB. So we have this B remaining. So I will put that B here, and XUB is nothing but KUB into D. So this will be B into D, isn't it?
Yes, sir.
And this divided by 0.87 Fy. So let me write that down, that this divided by 0.87 Fy. Fy. Now just look at this expression. Area of steel required to make this section balance is dependent on all these parameters. Can you identify the parameter which is dependent only on geometry in this expression? Will you agree with me that the parameter B into D is dependent on the geometry of the cross section, isn't it?
Yes, sir.
So this is geometry. What is the spelling of geometry? Double M है या single M है? Am I right, Shreya?
Sir, single,
Ah,
single mm. Single
oh,
mm.
okay. So let me delete this. Hmm. This is dependent on geometry. And what can you say about the remaining terms? FCK is the characteristic compressive strength of concrete. KUB is the neutral axis factor, which depends only on grade of steel. It doesn't depend on grade of concrete. So KUB is a factor which depends on grade of steel. FCK is the factor which depends on grade of concrete. And FY is the factor which depends on the grade of steel, isn't it?
Yes, sir.
So what can you say about these three terms? They are dependent on the material. Happy?
Yes, sir.
This BD is which geometric property? Isn't it the cross-sectional area? Do you agree with me? If I multiply this B by D, I get cross-sectional area, but it is not the gross cross-sectional area. It is the effective cross-sectional area, isn't it?
Yes, sir.
So therefore, what is BD? What do we call BD as? BD is nothing but AE, effective cross-sectional area, is defined as B times effective depth. Happy?
Yes, sir.
So this is the effective cross-sectional area and this is the material parameter. Now, what is the fun in having ASTP, which is function of the cross-section area? Instead of that, if I convert that into the percentage of steel, that BD will go away. The geometry will go away, isn't it? So if I were to calculate the percentage of steel, so let me write down that. So how do I calculate the percentage of steel? From this. So that percentage of steel, I am going to denote it as PT PST. Are you with me? Percentage of
Yes, sir.
steel, percentage of steel on tension side. S stands for steel, T stands for tension side, and P stands for balance section. So percentage of steel on tension side for balance section. Are you with me?
Yes, sir.
This will be equal to what? This will be equal to area of steel on tension side for balance section divided by, how do we calculate percentage? So this divided by the cross sectional area. What is the effective cross sectional area? It is nothing but B into D. Happy?
Yes, sir.
And this is a ratio, but to get the percentage, I will have to multiply it by 100. Happy?
Yes, sir.
So this gives me the percentage of steel for balance section. This is the expression for percentage of steel for balance section. Happy?
Yes, sir.
Now let me substitute ASTB in this formula. The moment I substitute ASTB in this formula, the BD in the numerator and this BD in the denominator, they will get cancelled, and therefore you will have PSTP equal to what it will be. It will be 0.36 FCK multiplied by KUB divided by 0.87 FY. Are you with me, Shreya?
Yes, sir.
This multiplied by 100. Happy?
Yes, sir.
So this is the formula that we have for percentage of steel for balance section. Now, can we have a tabular form uh, in which we will compute the percentage of steel for balance section for various grades of concrete and for various grades of steel. So let us do that. So what is going to be here? So I'm going to have FCK written here, and I'm going to have FY written below. So FCK will be written like this, and FY will be written like this. Happy? So let me compute. Let me write down various values of FCK. So M20. So FCK is 20 MPa. Then M25. The grade of concrete is, let us say, 25. So FCK 25. And then we have FCK equal to 30. This is what we have considered till now. Am I right? Or we have considered 35 and 40 as well. Shreya, can you check the previous table and tell me?
Sir, we have taken 35 and 40.
We have taken 35 and 40. So let us take 35. And we have started with 20, from 20, right?
Yes, sir.
So 35 and 40. So these are the various grades of concrete that we will be dealing with: 20, 25, 30, 35 and 40. And what are the various grades of steel that we are going to deal with? Those are 250, then 415, happy, and 500. These are the three grades of steel that we will be dealing with. And these are the 5 grades of concrete that we will be dealing with. Now, for Fy equal to 250, 415 and 500, do we have the value of neutral axis factor? Can you tell me the value of KUB for these three, Shreya? You can,
Sir.
look at
For
the notebook.
250,
Huh?
it is
For two-
0.53.
So I will just mention that here, 1 minute. So we have 0.53, 0.48
and 0.456.
and
456.
0.456. These are the values of KUB, neutral axis factor, mentioned for various grades of steel. So for 250 it is 0.53, then for 415 it is 0.48, and for 0.456, 500 it is 0.456. Now you have this formula here, percentage of steel. So what are the inputs in this formula? You have to substitute KUB and you have to substitute Fy and FCK. So in this table you have FCK, Fy and KUB. Substitute this here and complete this matrix. Tell me all the values. Okay, I will wait. So Shreya, this time you will tell me all the values. So calculate all these values one by one and tell me.
Yes, sir.
So first calculate it for FCK 20 and FY 250.
Yes, sir.
Hello,
Yes, sir.
are you done?
Just a second. Sir, it is 1096.
1096. No, it will be 1.96.
Sir, I'm getting it as
Correct. The
1.75.
1.9.
1 point?
75.
That's correct. 250 and 20, right?
Yes.
Chalo. So for this value is 1.75. Go ahead and tell me the other values. So how much is this value? 415 and 20. Quickly complete this table, then possibly we will stop for today.
Is 0.95.
Right? Uh, Yes. So now this table is complete. So for various grades of concrete and for various grades of steel, we know the maximum percentage of steel which we can provide on tension side. Are you with me, Shreya?
Yes, sir.
Okay. So we will discuss about this more in the next class. Let us stop here as far as this class is concerned.